Okay, we're moving on here now a little bit. We're going to still talk about some variables that we need to understand. One of those is pressure, and the next will be wind. There's a lot of things that influence pressure. But what is pressure, first off, I guess we should ask? It's weight per area. So what that means is basically it's on the average 14.7 pounds per every square inch. So if you think about how many square inches are on your body, that's a lot of weight. But that is the actual average pressure. If you were to take a standard atmosphere, that's the pressure in inches of mercury. So with that, we're going to talk a little bit more about pressure because think about it. The pressure at the surface is significantly higher than the pressure aloft. So the atmosphere would love to maintain the same pressure everywhere. In order to do that, it's going to move molecules, air, from one pressure that's higher towards low pressure. So if the atmosphere is lower pressure, the higher up you go, and it is, we know that from your air flying, for sure, something's got to be holding those molecules in. And what it is gravity. So there's something called the hydrostatic balance. All that stands for is that the pressure going up, that pressure gradient is balanced by gravity. And that's a very simplistic way of looking at why the atmosphere doesn't go flying out into the space. So with that, just want to talk a little bit about some more pressure things here in charts. So if you think about pressure, we want to know the pressure a couple ways. We want to know what the pressure is wherever you are. So if you're flying into Denver, you would want to know what the actual pressure is at the elevation of Denver. But you might also, if you're drawing a weather map, want to know what it is at sea level. So that means I've got to take whatever that pressure is at Denver and convert it to sea level. How do I do that? The simplest and easiest way is to use the standard atmosphere. If you do that, we can take whatever the pressure is at Denver and immediately get a surface pressure from that by reducing it by knowing the elevation. However, standard atmosphere doesn't always exist. So many times the corrections are applied due to temperature. So if you know what the temperature is in the lowest part of the atmosphere, you know what the elevation is, then we can come up with a much better approximation of what the actual sea level pressure is at Denver or at any other location. And there are various pressure patterns and all out there. There are also constant pressure surfaces. So let's take a look at a couple things here a minute. Here is the surface pressure currently. And you can see we have low pressure sitting out over the panhandle of Texas. Notice the myriad high pressures that are over the Rocky Mountains and all the higher terrain out here. This is where the issues begin with converting those elevations to sea level pressure. We wind up not being precise enough, maybe. So what you wind up with is a lot of sporadic pressures that are just slightly off. They're not off by a lot, but they're off by some, enough to cause this kind of a pattern when you do analysis of it. Now you'll notice there's a pretty strong low pressure well off the New England coast here. And if we looked at this in another way, we could actually see the sea level pressures at all these locations as well. Matter of fact, that over the Gulf of Mexico, you can see a couple here for 1014.6 millibars. Here is 1008.1 millibars, and you can see the 1008 millibar line going right through there. Now say I want to look at the same thing, but I want to look at it aloft. So we know that pressure is changing as you go upwards. So this would be an 850 millibar pressure chart. And what we're looking at here is contours. So that means that the 850 millibars, instead of being a flat surface as far as how high it is above the Earth, is undulating. And we can see that right here. And you can see that, well, a little higher, sometimes 700 millibars in this case, a little lower. And believe it or not, these kind of corresponds to high and low on surface weather maps. They're related. So looking at these pressure surfaces aloft can give us an idea of what is going on at the surface. And this pressure changes due to such things as temperature. So here's the pressure altimeter. You all probably are very used to these in airplanes, and you can set them. If you know the altimeter setting at the airport where you are and adjust it for that, there are some things that can throw it off. Maybe you didn't, moving along and you came to a different, wherever you took off, you had one altimeter and it needs to be changed in another place. Maybe you're flying through high pressure, which in this case would be 30.5 millibars, or not inches of mercury. So you wind up being actually higher than where you think you are. And here, flying into where low pressure is, you would actually be lower than where you think you are. And that's just based on pressure. Well, pressure is influenced by temperature as well. So say you're in a very hot atmosphere, we know the molecules are further apart, which means the pressure really doesn't change as fast in the vertical. So you wind up being higher a little bit than you would. And then when it's colder, you wind up being lower. So if you combine the two, say you're flying in a cold atmosphere with a lower pressure, you might be significantly off where you should be in your altitude. Something to remember when you're flying along. We're not going to deal with METAR code here. You can read through this very detailed. Density is another problem. You want a decent density to fly. In other words, if you have very low density, it's going to take a lot longer for your aircraft to build up speed and be able to get aloft. I know, for example, the deserts, Southwest, Phoenix, or Tucson, for example, in the summertime when they have 110 degrees, very low relative humidity, it's density is very much lower than a standard atmosphere. So it takes you a lot longer. If you have a really full aircraft, maybe you'll use the whole runway, or maybe you even need more, which has been an issue sometimes. And it's something that needs to be calculated, the density altitude. It's the altitude above mean sea level at which an atmospheric density occurs in the standard atmosphere. So it's basically corrected for non-standard temperature differences. So with that, let's move on from densities and temperatures. We're going to look at some winds. Pressure is the first thing you need to know to get wind. And wind means you have, and it can move in three directions. Air parcels don't just move in one plane, they move in all different directions. So which means that air parcel where you are may wind up somewhere totally different in a little while. And it may be higher, it may be lower, it may be north, or it may be south, east or west, any of those. In order to understand how the weather is going to change, we got to understand where that air parcel is going to wind up. So wind is both the motion and direction. So we need speed and direction. It's a vector. So it's the most complicated of all the atmospheric variables because of that. So we can measure it, and guess what? Winds at the surface are actually measured at 10 meters. So when you're flying into an airport, the wind you're receiving a report of is measured at 10 meters above the surface, or basically 33 feet. So that's not a wind at the actual surface on the ground, because of some reasons here. We'll talk about some of that. So what causes wind to move? Well, According to Mr. Newton, an object doesn't move unless there's a force applied to it. So, since an object is an air parcel, something must make that air parcel move or give it an acceleration. So that's the force. So what is the forces that work on air? Well, we could have pressure gradient, right? And maybe we could have friction. Oh, maybe there's a front coming together, pushing the air upwards or downwards sometimes. Maybe there's a mountain range. Each one of those is a separate force working on the air, that air parcel. All of those collaborate together to give you the wind direction. So we talk about pressure gradient force, Coriolis force, which is the motion of the earth, and friction. Friction really only impacts the lowest elevations, maybe the most 4,000 to 5,000 feet. So let's look at pressure gradient force. So if I have a bucket of water, like in this case, with high pressure, it's going to try to fill up the low pressure. So when I have a weather map like this one, these high pressures are actually pushing the air in towards this low pressure or this low pressure. So the atmosphere hates a pressure gradient. It's going to do everything it can to bring that pressure to normal. So air is going to move down the slope from high pressure into low pressure. Well, if it's moving down the slope, means it's moving towards or converging into this low pressure. So if air is coming together, well, since we can't go into the ground, it's got to go somewhere. So it's going to tend to go upwards. So that's why low pressures a lot of times have precipitation with them and clouds. And you can see here the wind speeds. In this case, you have 20 knots out of the north, almost northeast. Interesting. When you look at a station plot, remember the winds are coming from. So if it's, as you can see here, if you thought about a compass 360 degrees around this, you might say, oh, that's 01. So it's 10 degrees. It's coming from the northeast. Go further down here, you can see that is a southeast, almost southwind. Here's a due south. And these barbs indicate the wind speed. So 2 long barbs, each one is 10 knots. So you'd have 20 knots of wind. We can look at it a little differently here as well. But let's take a look at this one here a minute. I want to go over to another part here where we talk about Coriolis. If you're played pool, Coriolis impacts you more at the pole than it does at the equator. So if you're a super pool player and you have one tournament that's at the North Pole and the next day you have a tournament that's down at the equator, Coriolis is going to impact the way your ball moves. So you're going to have to make an adjustment to that. And as you can see here, you think the ball is coming straight at him, but it's not. It goes away from him because of the Coriolis impact. Now, if you did it at the equator, you'd see it go right into him. If you do it at the North Pole, you see it goes well away from him. That is all the Coriolis effect. There's something called a geostrophic balance as well, creating what they call a geostrophic wind. It has 2 components, the Coriolis and the pressure gradient. These 2 components, forces, equal. That's why the wind flows in a straight line. And you'll notice this more aloft. At the ground, there's a lot of friction that gets involved. So if I go back here, you'll see they're kind of cutting across isobars, right? And they're going towards low pressure. Now, if I go aloft, notice they're much more parallel, which is geostrophic wind. So there's not much as friction. And if I go even higher up, there's less friction. So if I was looking at a flight today, for example, coming across Texas, I know there's low pressure here. I also know my winds are coming out of the south here. And even up into here, they're southeast. But maybe at the surface, I might be getting some wind shear somewhere in here too. So maybe a more southerly southeast flow, southerly flow ahead of it, while at the surface, more in towards the low, more southeast flow or east flow. So there's wind shear that's developing in the lower part of the atmosphere as you're coming down for a landing in this area. So as you can see, pressure and wind kind of correspond, and pressure is related to temperature because of density. So we're putting all these variables together, and we're going to add some more here next week. So I hope you got a little bit out of that. Let me know if you have any questions.